Today we're going to create your own Euler circuit, convert a given graph to an Euler circuit, and solve weighted graphs.
Remember, an Euler circuit can be determined if all the vertices have an even degree. Degree of a vertex can be found by counting the number of edges that meet at that vertex.
For an example here, we have this vertex with 3 edges that meet at that vertex. So the degree of this vertex is 3. Another example here, there are 4 edges that meet at this vertex. So the degree is 4. So now we want to create our own Euler circuit with 7 vertices and 20 edges. Now I want exactly 7 vertices and at least 20 edges. You may need to use more than 20. So we have some vertices here. Just want to make sure we have exactly 7. 1, 2, 3, 4, 5, 6, 7. And now we need to start drawing some edges. So we'll take these edges, or take these vertices and begin connecting them. And typically you'll connect them in ways like this. So we've gone ahead and connected all these vertices with at least 20 edges. And the second thing you need to do is make sure you have at least 20 edges. So you need to count the vertices. The best way to do this is to put numbers on them, or maybe to identify them with a mark as you're counting them. That way you don't count one twice. So there are 21 edges as identified by the number labels given. And then the third thing you need to do to make sure that it's an Euler circuit is to make sure that each vertex has an even degree. And the way that you do that is you just count the vertices, or count the edges at each vertex. So we have 1, 2, 3, 4, 5, 6. So that's an even number. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this is an Euler circuit, and actually all the degrees are 6. That is kind of coincidental, but if you do notice, the number 6 is an even number. So each vertex has an even degree, which means that this is an Euler circuit. Next, what we want to do is convert this given graph to an Euler circuit. So the way that we do that is we figure out if each vertex is even or odd. So we have 4 for your degree for that vertex, 3 for that vertex, so that means we're going to need to highlight that one. 3 again. 1, 2, 3, 4, 5, 6. So that one's an even number. 1, 2, 3. That one's a 3. This one's a 3. 2 and 2. If you notice, each time there's one odd degree vertex, there will be a second one. And then we convert this to an Euler circuit simply by creating another edge that goes between the odd degree vertices. And that converts each one of these degrees into the number 4, which is an even degree. You can even be a little bit more creative if you really want to. You want to connect these two and go a little bit further, do a little bit more work. This is less efficient, but it is still correct. You connect that one and then back down to the odd. That changes this into a 6, which keeps it even, and changes these into 4s again. And then again, you can do the same thing as long as you keep all the vertices even. These change to 4s, and these change to 4s as well. Now, since each vertex is even, this is now an Euler circuit. And that's how you convert a given graph and make sure that it is an Euler circuit. And then lastly, we're going to be solving weighted graphs. The steps to solving weighted graphs are:
Number 1, add up all the weights in the graph. Number 2, identify all the vertices with an odd degree. Number 3, find the shortest route between each of these vertices. Number 4, make a second copy of each edge of that shortest route. Number 5, add the total of the weights from step number 4 to the total from step number 1 to find the most efficient total for that weighted graph.
So with step number 1, we got to add up all these weights. So when you add them all up, again, just like when you count the edges when you create your own graph, it's better to highlight or identify that you've already used that number. So when you add them up, you go 6 plus 5 is 11, plus 2 is 13, 14, 15, 16, 19, 22, 27, 31, 32, 35. So the weights in this graph add up to 35. We need to identify all the vertices with an odd degree. So here we have a degree of 5, because there's 5 edges, another degree of 5, another degree of 5, and because there's 3, there will be one more. This one here has 4, which means it's got to be this vertex. So there's all your vertices with an odd degree. Third, we need to find the shortest route between each of those, and because they're weighted, we need to find the smallest numbers that will allow us to get from one odd vertex to the other. So here we can copy this number, but we can also see that it's connected here with the number 1. So the number 1 is going to be the fastest between these two. And then between the next two vertices with an odd degree, our quickest route again is a weight of 1. Number 4, we need to make a second copy of each edge of that shortest route. So we already kind of have made that copy, but to be really literal, we want to make sure that we have the weights copied as well. And once we do this, we can add up the total of all the numbers that we have written down. But since we've already added the total in step 1 before making a second copy, we can then find the total of what we added and then add that to 35. So our solution to this graph is 35 plus 2. And the solution to this weighted graph is 37. So the last thing we want to do is take this weighted graph and find the solution for it. I'm not going to put the steps up. I'm just going to walk through it pretty quickly. So we want to add up the total numbers, the total weights in this graph, and you get 182. Then we need to identify the odd degree vertices. So there's 1. There's 1. There's 1. There's 1. Looks like most of the vertices in this picture are odd. Looks like every single one of them. So each vertex has an odd degree. And now we have to find the shortest route to connect each of these vertices. We're going to connect them 2 at a time. And we're going to start connecting them where we only have to duplicate the smallest numbers. So if we duplicate this 2, that's one of the smallest numbers. And then these 2 are now even. And we can move on to 2 others. The next smallest is this 3. So these 2 are now even. And now we have a little bit more of an issue. We can't connect this 4 because that would cause us to make this vertex odd again. So we got to skip the 4. And we're going to go to the next smallest number, which is 5. So we can connect these two. And then we need to try to connect the remaining 4 vertices with the smallest possible total. And here we have a decision to make. We can connect these two and add 20, but we can also connect these two, and that's shorter or less time or less weight than what we just did with the 20, because 9 plus 10 is 19. Or we can connect these two and 13, and of those 3 options that we have, this is the shortest or the most efficient that we have. And then we have to figure a way to connect the last 2 vertices. The easiest way to do that is to basically take a look to see if there's any way to do it that's less than a weight of 19. And any way you go, it looks like it's going to be somewhere in the ballpark of 30. So 19 is going to be the shortest route between those 2 vertices. Now we have made every vertex even. We have duplicated the shortest path between odd degree vertices. And now we have to add up all those weights that we just added. And I get 42. And when we add 42 to our original 182, the solution to this weighted graph is 224. Now there may be a possible solution with these weights that's slightly less than 224. If anybody finds that solution that's less than 224 and it's a legitimate solution, I'll give you an extra 10 points on a homework assignment. Now guys, that's solving weighted graphs, creating your own Euler circuit, and converting a graph that's not an Euler circuit into one.